That's a good question. So this platform will
Can you
support...
repeat the question real quick?
Oh, yeah. Which network operating system will this support? I'll take it a little further. Which software will this support, right? So this design will be supporting all the standard software that Celestica supports on their white box products. So that starts at the very low level with the ONI installer. So we support ONI. We'll support Open Network Linux as a Linux reference on top of this design. And then for a network operating system, this will support either Sonic or Dent, either one. No, sorry, I might not have made that clear. The 48-port design, the 48-port SKU, that has 16 ports of 2.5 gig. Yeah, so 16 ports of multi-rate gig up to 2.5, and the remaining 32 of 1 gig. The 24-port SKU is only 1 gig capable. Sure.
Any other questions? When will it? Yeah, when will it be available from Celestica?
Okay, so kind of the schedule for this, it's in development now. Samples probably towards the end of this year, and then production, early next year. Yep, you're welcome.
So what about the software on the Wi-Fi side?
Wi-Fi side, that's a section that we're going to align with partners on. So for the Wi-Fi and the LTE and the cellular stuff and the other advanced functions, whether it's a gateway or firewall, that stuff, we're going to look to partner with other entities to provide those functions and integrate those either with the Sonic or the Dent NOS that runs on it. So if there's any partners out there that provide those software pieces of functionality, we'd like to talk to you about that. Anybody else? Going twice?
Going twice. Sold.
All right. Thank you.
Sold. Thank you, Jeff. Well, we have a few minutes as we transition to our next speaker. And I know that, so we're actually running a little bit ahead of time, which is great because I'm sure that by the time we get to the end of the day, there will be a lot more questions. So please feel free to come on up. So for the next talk, as they get set up, also, both of us are going to be moderating this networking session today. So I'll be moderating for the first 4 talks, and then I'm going to be passing it on for the last 4 talks. And I'm always available for questions around the keynote. If you have any questions around the AWS specification or any other related topics, more than happy to field those questions. Okay, feel free to introduce yourself and your talk. Thanks.
Thank you. Thanks so much. Good afternoon, everyone. My name is Rohit. I'm a software engineer at Meta FBOSS team. This is a presentation that Eddie and I were supposed to give together, but he couldn't join in, so I would be giving it on his behalf as well for some of these slides. This topic is about scaling RDMA networks for AI training. The idea here is that basically, how did Meta evolve their RDMA deployments over the last couple of years for network AI workloads? It's our journey of what challenges we ran into, what problems we solved as we went along, and what are more challenges that are coming our way as we go along. We think our production RDMA network is pretty unique in many ways. We do all of these things where we build a network with commodity-based Ethernet infrastructure. We have a multi-hop class network, which we just assembled by using the vendor switches and put them together. it's native for AI workloads. What that means is that basically this network only runs specifically the AI workloads. This is tuned only for the AI training specific purposes. It runs on Rocky V2. It's a lossless transport. We use PFC and DCQCN as a way for us to make sure that it's a lossless network, and it uses the Ethernet underneath. And it's a large deployment at scale with thousands of endpoints running in a single fabric. Many such instances of fabric run today in our production environment. And we do all of these together. A high-level overview of the RDMA network, how it looks like on the Meta side. It's a class network, a two-level class network with the rack switches connecting to 16 GPUs, and they connect to the training spine switches, which we call cluster switches. We use routing in terms of, we're going to go more into each Xionyx server has 8x GPUs and 8 NICs, and they use the shared memory across, and they use RDMA fabric for sending traffic through across to different nodes. Let's look a little bit inside what the network pipeline looks like today. There was a tech keynote yesterday about network being one of the bigger bottlenecks when it comes to model learning and AI. And that exactly is true. And why it is true, let's zoom in a bit more on it. It's a snapshot of a trace of a run that is happening. And you can see on top there is compute that is happening. And compute is important, very important, of course. And then there is the collectives, the AI collectives that are running as well in parallel with compute. We picked up the more common AI collectives that are running today in our environment, which is all-to-all and all-reduce. To briefly mention, all-to-all is like a full mesh kind of a thing where all GPUs are trying to send traffic to all other GPUs. They use a full bisection bandwidth. All-reduce is more like an hierarchical kind of collective where it processes the data within itself and then creates a hierarchy with a kind of a tree kind of a thing. So it doesn't use a lot of network bandwidth, but this traffic is a lot more bursty in nature. And as you can see that basically there is an interlocking that happens where a compute cannot start until the certain collectives are kind of done, completed, which kind of puts network on the bottleneck or kind of on the long pole, because if the network is slower, then obviously the compute cannot keep going on in parallel and make progress. This is kind of a profile we did at a millisampler level on a 100 gig installation. And you can see the traffic on a 100 gig link is not always evenly occupying the whole of the bandwidth. It's a very bursty traffic. You can see there are bursts that come in and we start to hit the line rate, but at the same time, there is a lot of in-between times when the traffic is not that high. Makes things really interesting for us when we have to tune our network to account for it. So when we started building this fabric, the main challenges that we ran into, the first of all was a very low network flow entropy. What exactly the flow entropy is and why we need it is essentially because we have in past relied heavily on ECMP as a routing technology for us to distribute traffic evenly across the fabric. Low entropy prevents us from actually doing a very good distribution or equal distribution of traffic across the nodes. it has resulted in performance regressions for us, and we could not use ECMP and couldn't deploy it as our front or the primary routing scheme. Load balancing also became a problem, especially during network failures, which are quite common in any data center scenario. And the routing schemes that we try to build would kind of run into problems when there are switches above which are getting drained or the links coming down, kind of a thing. The other main challenge that we went into, which we kind of run into, is the performance when there are drops happening. Now, we try our best to make it a lossless network, but there could always be a bad optics or bad cable, which results in performance going down. And that's because of the go back N algorithm, which kind of severely hits the throughput if any main packet or a critical packet in the collective gets lost. Debuggability is another challenge. We'll go a little bit more in detail of it. The primary debuggability challenge we have is if a job goes bad, is it a network problem or is it an end node problem, kind of a thing. So the first challenge we ran into was network routing aspect of it and the load balancing. And as I mentioned, because of lack of flow entropy, we couldn't use ECMP. So the other alternative that we explored was the destination-based DPR. It's a deterministic path routing. What that basically means is we fix the paths of the flows, and each flow from one source to destination will take an exact same path through the fabric. That simplified things for us. The performance that we lost with ECMP was gained back, and things looked good. But the problem was, what if the links go down? We used essentially a full bisection bandwidth, and we used a subscription of 1-to-1. What that means is that downlink speeds and uplink speeds match with each other. So we have 16 downlinks and 16 uplinks at the same speed. And if there is any failures that happen on the uplinks, we cannot do this destination-based prefix routing anymore. We have to fall back to ECMP, and that results again in regression, which is non-linear to the fact that we lost multiple links in there. So static routing scheme did have its own limitations, and we also started running into the workload-related scheduling problems in our network. An example of a case of an oversubscription that happened was how the jobs get scheduled on these nodes. And there actually is not an uncommon case where a job gets scheduled where there are two jobs or two GPUs running on the same rack are trying to talk to the servers on two different racks, and they are using the exact same elevation or exact same destination routes. Since we try to use a deterministic path routing, we would kind of we will route based on the destination routes. And what could happen is that the two GPUs, the server 1 and server 2, are trying to send it on the same uplinks to server 3 and server 4. And obviously, we're trying to send double the bandwidth onto the uplinks, which were only supposed to carry like just 200G in this case, but were actually carrying 400G. This resulted in severe problems in our production. We started seeing performance dip. The AI job workload started to fail. Fallback to ECMP was a similar kind of a problem. Essentially, you lose 2 links. Now you have 16 downlinks and you have 14 uplinks. You're trying to send traffic for those 16 up to the 14, and you basically run into that problem where there's not enough bandwidth going up. But more importantly, the bigger problem is that now we have to fall back to ECMP, and we run into the hash collisions, which result in non-linear degradation of the performance. So what kind of solutions we started exploring once we hit this problem? We went with the even rack placement for job scheduling. What that meant was we tried to overcome the problem of oversubscription on the uplinks by making sure the jobs run on certain racks in certain order. That is more like a mitigation because we would not be able to fully use all our racks to run the jobs if they don't align properly, and that resulted in wasted resources for us. So it was anyways not a long-term solution for us. We try to realize more entropy in the existing workloads. We used a queue-pair multiplexing mechanism that is allowed today by the workloads. It allows more entropy into the system. We used customized hashing schemes to extract more out of it, so we could use eCMP as a better or more effective mechanism when the backup plan kicks in. We have also been playing with traffic engineering side of things. We're using software-based controller to program routes, and based on the demand and the job scheduling, we're able to change how they send traffic across to different nodes. Spray, reorder, and assembly is another option or another direction. In yesterday's one of the tech nodes, keynotes, this was actually kind of referred to as well, that spray or reorder can actually, the spraying of traffic can result in a very balanced, utilized network, but it comes with its own challenges in terms of reorder and assembly. There are two approaches again in there. You could use something like an in-network reorder and assembly, where you spray the packets on one layer, and on the other layer you kind of reassemble them so that when you go to the endpoint, you are essentially just distributing the traffic as it is and is not out of order. The other kind of solution is you actually spray the packets and they are received on the NIC side, but they are out of order. And out of order delivery can be tolerated somehow on the NIC side. So that's another kind of a solution that we have been exploring. Interestingly, in all this stuff, we thought there were some challenges we're going to run into, which we did not run into as significantly, which didn't turn out to be as big of a pain. We thought we're going to run into a lot of head-of-line blocking with PFC. We did not. And likelihood, the reason that we didn't run into it was because of the deep buffer switches we use on the level 2 hierarchy here, or in the second level clause. We used the static card buffers, which did not affect other ports when they went down and so on, and it kind of helped mitigate any pressure on the buffers that could happen on the uplinks, on the CTSW or on the second level switches. We put the PFC watchdog in place because there is risk of we running into PFC loops. That didn't happen either, fortunately. Scaling large node job could be a problem, but we didn't hit that kind of a problem specifically because most of the newer NICs do not run into these QP cache limitations that we thought we may hit into. And in the end, we thought that DCQCN was going to be like the main thing which is going to help us tune the congestion control. PFC seems to do the trick for us. We rely more on PFC. We have DCQCN in there, but what we have found so far is that this is just the congestion control. Basically, DCQCN hasn't been able to help as much as we thought it would, and PFC has been able to just control the whole network performance and throughput. So our last and most important challenge that we ran into is obviously the debuggability of the system. Once the system is up and running and sending traffic, there is bound to be problems that's going to happen. So basically, the main problems where this stems from is the fact that the AI workloads are very sensitive to loss. And the reason for that is because we use go back and routing scheme, where if one packet gets dropped, the receiver asks for all the traffic that was there in the last n window to be sent back to it. That's obviously for the reason that it assumes the network to be lossless, kind of a thing. It's challenging to narrow down the disruption to network or non-network root cause. If your job fails, how do you figure out it's a network or it's an endpoint problem? We obviously rely on several network metrics to get such signals, like out-of-sequence packets, congestion metrics, pause durations, and so on. But they kind of have their limitations in the sense that they won't be able to help us all the time in all the cases. Performance is also sensitive to endpoint issues, as we just talked about, and they are harder to narrow down as well. Imagine there is a 128 GPU job running, and one of the GPUs is slow or bad. How do you actually figure out who is the bad apple among all of them? So it becomes hard, especially when the job failure points to multiple timeouts happening on multiple GPUs. How do you actually figure which is the bad one? Over the time, we have been using several debugging tools. We developed some of those tools as well. We resort to active monitoring in some cases where just before AI workload starts, we kind of run the pre-flight checks to ensure that we do not have any network issues or GPUs are running fine, kind of a thing. It's more like a sanity before we actually start those AI workloads. There is a pinger support. There is a constant UDP and RDMA pingers that we have running inside our network, which ensure the connectivity of various nodes from the network perspective. And then in the end, we also have tracing and GPU traces to kind of help us narrow down where the problem is coming from. So just a quick recap here. Essentially, we have a scaled Rocky V2 workloads which have very unique constraints, and that's because of the unique demands that we have put in there. Because of these unique constraints, we have run into unique operational challenges as well. We have been able to scale the commodity Ethernet RDMA deployments. Obviously, multiple challenges still remain, and there are many directions to kind of find the solutions with no perfect solution in there, and multiple solutions having their own trade-offs. So call to action here is that as a community, we could collaborate on unified solutions. We don't have to keep solving the same problem over and over, kind of a thing, and be able to leverage the expertise or the experience that we have learned on our networks across, kind of a thing, into the community. And of course, the debugging tools can be improved. They can get better, and we can definitely help with collaborating on those tools so that we can actually isolate the problems in a faster manner.
Okay, thanks, Rohit. Any questions? Again, you can shout them out from the audience, or there is a microphone in the back.
Questions?
Any questions?